Okay. Okay. Morning. I'll continue to discuss some analogies between knot theory and number theory. Today, the first is we discuss the Alexander Fox theory and the Masanori theory. So first, knot side. Let K is a knot in the 3 manifold M. This is a knot. And the 3 manifold, this is a closed, connected, oriented 3 manifold. And I assume that K is null homologous inside M. Closed 3 manifold. I assume it's connected and oriented also. And xk is a knot complement. By this assumption, and the homology group of the knot complement is the sum of the infinite cyclic group generated by meridian with some finite abelian group. This is isomorphic to Z. Yep. Okay, so here is a picture. So by this component, would we have the unique infinite cyclic group, infinite cyclic covering of xk. This is infinite cyclic covering. So the Garo group of this cover is the infinite cyclic group generated by this gamma k. So we have the unique n-fold cyclic cover. This is n-fold cyclic covering. And knot complement is in M. So then this is it's a well-known fact in the knot the topology. As we can complete XM to some closed manifold Mn, and the Mn is a cyclic covering, n-fold cyclic covering, a branch cover as a branch over K. This is branch covering. This is the unramified covering. This is the usual cover. This is branch covering, branched over K. Okay. Now, let lambda be the group ring of the Garo group of xk infinity of xk. So this group ring is identified with the Laurent polynomial ring by identifying the generator of the Garo group with t, the variable t. Okay. Then the homology group with infinite cyclic cover is naturally it's a lambda module because the Garo group acts on the here, so the acts on the homology group. This is I always consider the coefficient z, z coefficient homology group. Then the first well-known theorem in Alexander Fox theory is that H1 x k infinity is a Noetherian a torsion lambda module. And the initial elementary ideal, the topologists call it elementary ideal, but algebraists call it fitting ideal. Of H1 xk infinity is generated by the Alexander polynomial, where the Alexander polynomial is defined by the characteristic polynomial of the gamma k acting on the infinite cyclic covering, the homology of infinite cyclic covering. Okay. This is a well-known fact. Okay. And also, the following is well known. The homology group of the branch cover is isomorphic to the quotient of the homology of infinite cyclic cover divided by the axiom of the gamma k to the power of n minus 1 of xk infinity. This is well known fact for any n. Okay. So by the theorem 1 and theorem 2, we have the formula for the order of the homology of the branch cover, which is given by the product of the absolute value of Alexander polynomial evaluated at zeta is the root of nth root of unity. Okay. This is just algebra. Like this and this, and we have this formula. This is a simple algebra, the resultant, using resultant formula. So by this formula, we easily see, by the elementary calculus, let's compute 1 over n, the log of the order of the homology. Let's compute this one, the quantity. Okay. Then by this formula, this is 1 over n, and the sum of the log of the absolute value of Alexander polynomial, the value of Alexander polynomial at nth root of unity, just right, just we put here in here, so right, and then this is simply rewritten as k equals 0 to n minus 1, the log of the delta k to the e to the 2 pi square root minus 1k over, sorry, let me write this, not k, this is just maybe j of n. Now this is the nth root of unity. Right? So this is root of unity. Then by the calculus, on the high school calculus said, if n goes to infinity, then this is the integral of the log of the delta k of the e to the 2 pi square root minus 1 x dx. Right? And this is the so-called Mara measure of delta k. It's Mara measure. Of the Alexander polynomial. So hence we get the formula, asymptotic formula of the homology of the branch cover is some constant times e to the power of the n times Alexander of the Mara measure of Alexander polynomial. Okay. Okay. maybe I should write here. So the prime case. Now next I will discuss the prime case. So the K is number field, algebraic number field of finite degree over rational, and we fix the P is in prime number. Okay, and like K infinity over K is a cyclotomic ZP extension, and I assume that there exists a unique prime of K over P, and this P is totally ramified. In the cyclotomic ZP extension. This assumption corresponds to this assumption because in the knot case, the knot is always totally branched. Yeah, knot is always totally branched. So we assume that the same thing for the arithmetic case. Then the situation becomes very nice, and we have the totally exactly parallel story with the not series side. So now it's the situation. So let lambda hat here is a completed group ring of the Gara group of the cyclotomic. Let's say it's the Gara group. So we have the situation is K infinity over K, and the Gara group here is generated by the Iwasawa monodromy is gamma p, and this is isomorphic to ZP in this case, and like Kn here, this is a p to the nth degree is a cyclic sub-extension, intermediate extension in the cyclotomic ZP extension. Okay. And in this case, let's Hn is a P0 subgroup, P part of ideal class group. Of Kn, this one, and H infinity, which corresponds to the homology group of infinite cyclic cover, is defined by the project limit of Hn with respect to the norm map of ideal. Now, let lambda hat is a completed group ring of the Gara group of infinite cyclic, cyclic ZP extension. This is completed group ring, which is identified with the former power series ring over ZP by identifying gamma p with 1 plus t here. Note that this is a little bit different, but this is a common thing. Then this is one. This is called the Iwasawa module. Which correspond to the here the homology group infinite cyclic covering. This is called the knot module. So knot module correspond to Iwasawa module. Or sometimes this may be called the Alexander module. This is Iwasawa module corresponding. Then H infinity is lambda hat module, because the Gara group act on the K infinity, so they act on the Kn. in a compatible way with norm map. So the H infinity is a lambda hat module. Then the first well-known theorem maybe 3, by Iwasawa. I don't like Iwasawa, maybe it's well known, that H infinity is a Noetherian. The torsion lambda hat module. And the initial fitting ideal is generated by the Iwasawa polynomial, which is defined by the characteristic polynomial of the Iwasawa monodromy acting on the Iwasawa module. Okay. Also, by theorem, by our assumption, the intermediate P ideal class group Hn is isomorphic to the Iwasawa module divided by the gamma to the power of the P to the n minus 1, P to the n minus 1 over H infinity. This is also Iwasawa's theorem. And also the proof is totally perfectly parallel. So the thing, this corresponds to theorem 2. And by this theorem, can I write here? Sorry. By this theorem 3 plus theorem 4 imply that the order of Hn is given by the product of the periodic absolute value of Iwasawa polynomial evaluated at p to the nth root of unity. So by this formula, not like this. This is Iwasawa's computation. By this formula, we get the so-called Iwasawa's asymptotic formula. P to some maybe nu p to the n plus lambda n plus nu is lambda nu is the constant independent of n, but it's a conjecture. It is conjecture that nu is always 0. So if this is nu, it's always 0. So we have the similar formula for the case of the knot. So Mara major corresponds to the lambda invariant, and in the cyclotomic case. So, okay, this is a classical story. Now I finish, I think, the basic, to discuss the basic analogy between knot theory and number theory. Okay, these are all classical things. But today, I think this is the final. This is the last lecture. So I'd like to talk about my most recent work. This recent work. So my recent work is universal deformation of knot group representation. For knot group representation. This is a joint work with Yuji Terashima. The Tokyo Institute of Technology. Because there is many problems as on the analogy between Iwasawa theory and Alexander Fox theory, but basically it's based on this analogy. So okay, now I would like to go non-abelian direction, which generalize this analogy between the Iwasawa theory and Alexander Fox theory. This thing is generalized this classical analogy in the direction of non-abelian extension. What style we developed the general theory? This is general nonsense, not nonsense, general theory, general group theory. And this is maybe viewed as a discrete analog. The analog for a discrete group of so Weierstrass theory for the profinite. They discuss, their theory is about a profinite group. Actually, it's for the Galois representation, but here is the theory is about for discrete group. So let G be any finitely generated group. And this is going to be the not group later. This is going to be not group. But this theory, this general theory, can be applied to any finitely generated group. So if you like Klein group, maybe Fuchsian group, you can apply braid group, it's okay. So any finite group, generated group is applied to this, the following story. That A is any commutative ring with identity element. That N be the integer, the positive integer. Let me see. So now maybe I should write. Here is definition. The map, this map of T from G to A is called a pseudo representation of degree n if T of identity element of this one. Sorry, maybe I should. This is different of this. This is the identity element of group G. Group G is n, and T of GH is T of HG, or any G, H, and G. There is three conditions. This is the second one. The third one is sum. This is the third condition. This is 1, 2. Third condition is sum over. This is a symmetric group. Symmetric group on the n plus 1 letters, and signature of sigma and T sigma. I define this soon. 0 Gn equals 0. Where sigma n plus 1 is a permutation, the symmetric group, permutation group on the n plus 1 letter 0, 1 to n plus 1. And for such a permutation sigma, which is a product of the disjoint cycles I11, I1, K1, IM1, IMKM. This is a product of disjoint cycle. And we include the length 1 cycle, so that's the sum of kj, j equal 1 to m, must be n plus 1. And I11 should be 0. For any is the permutation sigma given by this expression, and the T sigma is defined, T sigma G0 to Gn is defined by the product of the j equal 1 to m and the T of Gi1, Gij, 1, Gij, Kj. Okay. This is the definition of T sigma. Actually, this property is, I think, axiomatize the property of the character of the representation. So the basic thing is, example is if rho is a representation, a degree n representation over the ring R, is if this is a homomorphism, this is representation, then excuse me? Oh, yes, sorry. For any G, so this is a group in G, element of G. Sorry, not this is not. Yes, this is one. This is okay. This is okay, but this is a product of the group. Then the trace of the representation is actually a pseudo representation. Representation of degree n. This follows from the well-known theorem by Processi on the invariant theory of matrices. This notion was first introduced by Wiles for degree n case, degree 2 cases, but he used some other complex conjugation. But in general case, this notion was introduced by Taylor for profinite group and continuous rep. For their case, it's the G is profinite, so everything the map will be the map is continuous. But here G is a discrete group, so we don't take the continuity into account. It's we don't take topology into account. Everything is discrete. Okay, this is a pseudo representation. Now, let F be a field, a fixed field in the following, and let O be the bit ring of F For example, if f is z mod p, then the O is zp, periodic integer. If f is the complex number field, then O is formal power series ring, one variable is here. And the later, I'll take f to be complex things, number. Okay? In the arithmetic case, it's always we consider the fp and zp. But I'll take complex number in later for the application to knot theory. Okay, we fix this. We fix these things. We fix this in the following. Now, definition. Let t bar from G to F is a pseudo representation of degree n. And we call the pair of R and T is called the deformation of T bar. Deformation of T bar if R is a local O algebra with residue field, MR denotes the maximal idea of the local field. So residue field is a given field F, the given field F. And T is a pseudo representation over R of degree n such that T mod maximal idea over R is given T bar. So this is the infinitesimal deformation of T bar. And also we call the R tilde and the T tilde is a universal deformation of T bar if R tilde and T tilde is a deformation of T bar, and for any deformation RT, we have the following universal property. They exist uniquely. The phi is local O algebra homomorphism. The local O algebra homomorphism such that phi is composed with rho T tilde is T. So the universal deformation is just a universal one among all deformation of pseudo representation. Okay. Now, our first theorem, for any pseudo representation, T bar G to F, there is if there is such a universal deformation, there should be the unique, because by the universal property. There is a universal deformation. R tilde and T tilde of T bar. Okay. I won't prove this. This is just follow the proof of Taylor. That's for the profiling case. Yeah.
So it works because of ring A was actually a field. So there was the ring A was the definition of the triple representation. You take the A, which is any of the rings. So in the case when it is a field, it is working, but for other rings, it doesn't work.
Which one?
A. So
Yes,
the
yes.
target of the pseudo representation is now a field.
Can be any commutative ring.
So here the theorem is still true for any commutative ring.
But but how do you formulate here? It's but we have to have the local O algebra.
That's right. So
You mean if you replace F to be by A, then what do you take?
so definition itself is not quite well defined.
This should be all local algebra. And if you reduce to their residue field, this must be their given one. So if you take a F to be any
Can we begin with some local ring from the first place and maybe then?
here?
Yes. Instead of F, if I take a local ring, then
F is local ring. Yeah?
still okay. So it's still not making too much sense. Okay.
Yes, but maybe this is maybe immature definition, but I just defined recently. So, but what in my mind is just this example, this example. Arithmetic case is this example. Okay. I don't know. Actually, I'm not. But it's okay. The story goes well. But I've just defined things recently, so maybe it's better formulation can be. But I think I just follow the Taylor's one. So this is theorem 1. That's okay. Now it's I'm going to the universal deformation of representation thing. So to formulate the things, I'll introduce some basic notion. Suppose rho and rho prime is a representation of G to any local ring here now. This is A is local ring. Is local now. Then the rho is said to be the strictly equivalent to rho prime. This is well-known notion in the deformations, the Galois deformation theory. There exists X in the I. This is identity matrix, and Mn, Ma. So if we reduce, if we take the modulo M A, this becomes the identity matrix. Okay, so such that, and rho, here the rho prime G is X inverse rho G and X for any G. G. This is strictly equivalence. Then I define the deformation. Okay. Suppose rho bar is a given residual representation. This is a residual representation. GL and F is a given representation. The F is this way. F is this F. Then the pair of rho and R and rho is called a deformation of rho bar if R is sorry. I'm sorry. I should put here the completeness. Sorry. Complete. Completeness assumption should be needed in the later discussion. The complete. Actually, the Henzelian is okay, but I just complete. Henzelian is fine. Henzelian is fine. R is a complete local O algebra, and rho is a representation of G over R, degree n, such that rho mod MR is the same. Here is the same as rho bar. Is the same as rho bar. And I define the universal deformation rho bar as follows. The pair of rho R tilde and rho tilde is called the universal deformation. Of given rho bar if R tilde this pair is actually deformation of rho bar and satisfies the universal property. So for any deformation rho of rho bar, there exists C is R tilde to R is a local O algebra home such that C composed is rho tilde is strictly equivalent to this rho. So it's deformation is in a sense a strictly equivalence class of deformation. Okay, so deformation is in a.
Do you also suppose that the radical field of R is?
Sorry, yes, right. You are right. Thank you. You are right. Yeah, sorry, I forgot this. Radical field F should be F. Then we have the following theorem. This theorem to this connect the deformation of the pseudo representation. Suppose rho bar is a residual representation which is absolutely irreducible. Absolutely irreducible. That means this is irreducible over the object closure of F, absolutely irreducible. Then the correspondence from rho to the trace of rho gives the following bijection. A bijection from the equivalence class of deformation. This is deformation, strictly equivalent class. This is deformation of rho bar to pseudo representation. Yes, sorry, we fix R. Sorry, here we have to fix R. Here, sorry, I should write here the fix here, and this is absolutely irreducible. And R is a complete local O algebra. Then the map given by trace gives a bijection of the deformation of rho bar to the deformation. This is deformation of trace rho bar over R. I don't prove this. This also the same force works for the case of in the case of the profinite group. The essential thing I just mentioned. This is I think well known to use cell Carroll lemma. Then using this theorem, this theorem plus the so-called Nissen theorem. Here we need to the complete initial assumption to apply Nissen theorem, but I don't know. I don't like the Nissen theorem. Anyway, it's using these things. It's we get finally we get existence of universal deformation. This is a way to show the existence of universal deformation by Taylor, but originally the Mazur's proof is different. He used a more functorial approach. But Taylor's one is better for our purpose, to application, not theory. It's very concrete. The theorem 3 is that for any absolutely irreducible representation of rho bar G to GLN F, there is the universal deformation R tilde of rho tilde of rho bar. Okay.
So
Yes.
here the deformation of representations, the universal deformation is also determined up to this strictly equivalent.
Yes, strictly equivalent.
Okay, so it's not unique.
Yeah, in that sense, in that sense, it's not. Yes, deformation is defined up to strictly equivalence. And okay, and the remark I should remark is following remark is of order. Actually, for the application to knot theory and geometry, often we use often the representation we have is the SLN representation. So determinant is fixed. So for that, it's so as for if the given residual representation is SLNF, then the SLN deformation and the universal SLN deformation are defined similarly. Are you okay with this line? Just change the GLN by the SLN. So nothing. I don't repeat that definition. So define this. Then just mark this. Then the theorem 4 is for any absolutely irreducible representation rho bar of G to SLN F there is the universal SLN deformation. Let me call it R tilde 1, just R tilde 1 and rho tilde 1 of Rover. Okay. This R tilde 1 is simply is the R tilde, the quotient ring R tilde of the determinant of the rho tilde G minus 1. This is the same, it's a Gara representation for same as a Gara representation is this. So, okay, this we have the universal SLN deformation. Now this is a general, just general thing, general theory. But I apply this to the knot theory.
Theorem 3, the existence of universal deformation ring is intrinsic, or do you have complete algorithm?
It's a good question. How to say? It's a good problem to find a universal deformation ring explicitly. It's a difficult problem for the case of Gara representation. There is some, difficult. In general, it's, in general, it's difficult. But for the knot case I discussed now, is we can give the explicitly that using some other information things. In general, for general or finite genetic group, it's difficult to give a concrete description of R tilde. But this R tilde is the same as universal deformation ring for pseudo representation. But for pseudo representation, we have some algorithm, but it doesn't work. We have to it's infinitely many variables first and divide. It doesn't work. Okay, this is a general theory. Okay, then application to knot theory. Is that suppose K is a hyperbolic knot in S3. S3, and GK is a knot group. Okay, as I said, it's a knot group. I always have some analogy between knot group and Gara group, prime group. So let rho bar is a holonomy representation. I talked about in the colloquium. This is a holonomy. Actually, it's a lift of holonomy representation. Holonomy representation takes but yes, for holonomy representation here, this target to be the PSL2C, but we have to lift that, lift of the holonomy representation. Associated to the complete hyperbolic structure on the knot complement. As I said, this is a complete hyperbolic three-manifold of the finite volume. And then we have associated holonomy representation. And it's known this is absolutely irreducible. This is irreducible, actually. This is irreducible. This is known fact in topology. Okay. So now, for this cases, we take F to be complex number. So O is a formal power series ring. One variable over C. Then by theorem, our theorem 4, there exists uniquely up to the strictly equivalence class, universal SL2 deformation of rho bar, say rho tilde is a GK to SL2 R tilde 1, that notation. By applying general theorem, we have a universal SL2 representation of the holonomy group, holonomy representation. Then our theorem 5. This is the theorem 5 we proved recently, is that this R tilde 1 is isomorphic to the formal power series ring one variable over all. So in this case, the R tilde is given explicitly. And the proof is it's a use geometry. Use basically Thurston theory. Or on hyperbolic geometry. So I don't want to prove this one. Thurston theory on in the topology student maybe known the Kyushu theory. To work, I use Kyushu things. But the following remark is of order. Okay. Now it's rho. So now rho tilde is representation, not a group. Universal deformation is GK to the SL2 O X, one variable formal power series ring. But if you restrict rho tilde to the peripheral group, the peripheral group is a fundamental group of the boundary torus of a tubular neighborhood, tube neighborhood. This is tube neighborhood boundary. Then the decay is simply the abelian group generated by meridian and longitude. So this is conjugate to the some upper triangular representation. Okay, this, so we have this, because this decays as abelian. So this is a situation similar to the ordinary deformation in the Gawa representation. So our theorem actually analog of Hida's deformation, modular. Maybe we don't need modularness because now we have a Taylor-Wiles theorem, but modular deformation. Which has a following form. Often, in general, it's a bit different. Often the GP is a profinite. It's a pi round of spec Z minus P to the GL2, in this case, GL2 ZP formal power series ring. In general, the universal ordinary deformation ring is not like this, but often becomes this something. And yes, and here, as if this is here, if you replace x to be the C, 1 plus P to the some power W or minus 1, then we have a representation rho W is C composed with Hida's representation is GP to GL to ZP. Okay, this is Hida's representation actually interpolate the all these representation. This is Green representation associated with the modular form of weight W, if W is integral. Okay, so Hida's representation interpolates Green's representation of modular form. So W is a weight parameter. So X is actually the weight of the correspond to the weight of periodic modular form. But our case is our case is a similar thing that happened. Our case here in theorem 5, again here in theorem 5, if X is replaced by now in this case is a trace of rho z, yes. In theorem 5, let dk is a deformation space of a hyperbolic structure. Hyperbolic structure I discussed in the colloquium. Then we take the deformation hyperbolic structure rho z. Then z defines the holonomy representation. Actually, this z is correspond to this w weight, and this d is correspond to the so-called dense surgery coefficient. Deformation space actually, deformation space is a space of dense surgery coefficient. So z. Then if we replace x to the trace of rho z of meridian, alpha is meridian. Then we get, if this is C, we have a representation reading rho z, which is C decomposed universal deformation, which gives a representation of the knot group to SL2O. Okay. This is a holonomy representation associated to dense surgery coefficient Z. So our representation, our universal representation is interpolating the whole holonomy representations. It's quite similar to that here, that Hida's theory. Maybe that's it.